All right, guys, in this lesson, we're going to be looking at tests of significance. So, when we think about tests of significance, there's a few things that we need to do. And again, this is based off of that four-step process. We need to make sure that we include our state portion, which is to identify the population and parameter of interest, and then we also need to state the null and alternate hypotheses. So both of those will take place in the state portion of the problem. From there, we need to verify that the conditions are met. This is the plan portion of the problem. So we need to check for random, independent, and normal. Okay. Then from there, we need to complete the do portion. And so we need to name the test. So basically whatever function you're working with in this case is going to be the name of the test, or the function from the calculator that you're working with. We need to calculate the test statistic and p-value as well. So you want to make sure that you include the test statistic and p-value and name of the test all in that do portion. If you do this in the calculator, the name of the test will be taken care of when you list what function you used in the calculator. Then you need to include either whatever the test gives you for t or z, depending on if you're looking at a mean or a proportion test, and then you need to list the p-value as well. And then finally, you need to conclude. Okay, so you need to interpret the p-value in the context of the problem. You need to make a decision about the null. That's how you do this. Make a decision about the null, and then you need to state evidence for or against the alternate. The alternate hypothesis is what you need to include, or what you need to make a decision on based off of your null hypothesis. So you need to include something that has to do with the alternate hypothesis in this case. So I would highly suggest writing this down for tests of significance, because it needs to be included. All of that needs to be included for this, okay? We also have our type 1 and type 2 errors and power as well. So our type 1 error is when we reject the null hypothesis, that is true. And then our type 2 error is when we fail to reject the null hypothesis, that is false. I would use this table right here to help you remember that when your null hypothesis is true and you reject your null hypothesis, that is a type 1 error. When your null hypothesis is false, so when your alternate is true and you fail to reject the null hypothesis, then that is a type 2 error. Power is how well a test will detect a type 2 error, and you increase power by increasing the sample size or increasing the significance level. How I like to think about this is something along this line. If you want to, or just power in general, really the only questions that I've seen about power have been how its relationship to the significance level or the sample size itself. So if you increase your significance level, then what that's going to do is it is going to increase your power. It is going to increase your probability of a type 1 error as well, though. And it is going to decrease your probability of a type 2 error. Okay? If you decrease your significance level, what that's going to do is, actually, I'm going to erase this. Hold on one sec. I'm going to erase this and set that equal to, if you decrease your significance level, that is going to decrease your power. It's basically going to have the opposite effect. It's going to decrease your probability of a type 1 error, but it's going to increase your probability of a type 2 error. Okay? However, if you increase sample size, what that's going to do is it's going to increase your power as well as decrease both probabilities of a type 1 and type 2 error. So, The safest way to increase power, essentially, or what they're trying to get at is the safest way to increase power is to increase the sample size. However, if you do increase the significance level, you can do that. That will increase power, but at the same time, it will also increase your probability of a type 1 error as well. So that's just kind of what's important to know. But that's the relationship between increasing and decreasing significance levels as well as sample sizes itself. So let's go ahead and look at these tests for proportions real quick. So we have two different kinds of proportions that we can look at. If we're given just one proportion in the problem, then we're just running a test for one proportion. If we're given two proportions in a problem, then we're running a test for a difference in those two proportions. So when we're looking just at the mean of that proportion, the mean of the sample proportion is going to be whatever population proportion that they give us in this case, or whatever sample proportion they give us in the problem. The difference in those two is going to be the difference from proportion 1 minus proportion 2. Our sample standard deviation based off of proportions is going to be the proportion that we're given times 1 minus the proportion divided by the total number in the sample, and we take the square root of that. The difference in proportions, or standard deviation for that, would be, again, we're adding, not subtracting in this case. So the proportion from sample 1 times 1 minus the proportion from sample 1 times the total, or divided by the total number in sample 1 plus the proportion 2 times 1 minus proportion 2 divided by the total number in sample 2. Then we take the square root of all of that, and that gives us our standard deviation for difference in proportions. So in this example, we're given, it says a union spokesperson claims that 75% of union members will support a strike if their basic demands are not met. A company negotiator believes that the true percentage is lower and runs a hypothesis test. What is the conclusion if 87 out of a simple random sample of 125 union members say they will strike? So again, we run through our 4-step process. We state first, or excuse me, that should be much longer. That should go all the way down here. We say that the parameter is the true proportion that will strike out of all union members. Our null hypothesis is the proportion that we're given right here, 75%, so that our proportion is equal to that. Our alternate hypothesis is basically saying that our proportion will be less than 75%. And we get that by saying 87 divided by 125. So because 87 divided by 125 is actually a proportion of 0.696, that's how we determine what our alternate hypothesis would be, is that we're checking to see if that proportion is less than 0.75 based off of our sample in this case. From there, we would complete our our plan portion. Gosh, go back. Our plan portion. So we are told that the sample is a simple random sample. We can assume that 87 is less than 10% of all unions and union members, and we can say that the sampling distribution is approximately normal because the large counts condition is met. So we would take our total sample, 125, times 0.75, and that gives us 93.75, which is greater than or equal to 10. 125 times the proportion for failure, or 1 minus 0.75 is going to be 0.25, and that's 31.25, which is also greater than or equal to 10. So that checks our large counts condition. Again, make sure that you are actually doing the math and showing that it is normal. From there, we want to complete our do portion. So from this, we can do this basically based off of this right here, or safest way to go is the calculator in this case. So you can go to stat, tests, or arrow over to tests, and what we can do is we can find the 1 proportion z test. So 1 prop, that's a terrible one again, 1 prop z test. Okay, make sure you're including a test because we are looking at tests of significance. So for p of 0, what we would do is we would put in 0.75 for this case. Our x value is going to be 87. Our total number in our sample is going to be 125. So 87 and 125 to make sure that this works. We are checking to see whether or not it is less than our actual proportion, our P of 0, basically. So we're checking the alternate hypothesis is less than our null hypothesis in this case. So that would be less than P of 0, and then we would calculate, and that should give us what we need as far as our Z value right here, which is negative 1.394, and our P value, which is 0.0816. So because they don't give us a significance level, we assume that it is 0.05, so we would say that since 0.0816 is greater than 0.05, we will fail to reject the null hypothesis. There is not convincing evidence to believe the proportion of union workers who will support the strike is less than 75% in this case. So, building off of that example, two questions. What is the probability that we have made a type 1 error? Well, since we used a significance level of 0.05, we would say that there is a 5% chance that we would reject a null hypothesis that was actually true. And then if we are asked what is the P value in context, or what is this number right here, 0.0816, in context, what we would say is if the proportion of union workers who would support the strike is really 75%, there is an 82% chance, or an 8.2% chance, that in another sample of 125 workers, we would see a proportion this far or further away from 75%. So essentially, how you think about interpreting a p-value in context is you would state the null. So if the null was true, there is an p-values chance that another sample of size n, 125, we would see that proportion this far or further away from our null itself. Okay, so if the null was true, there is a p-values chance that we would see another sample of that size that far or further away. Let's look at another example here. So suppose that early in an election campaign, a telephone poll of 800 randomly chosen registered voters shows 460 in favor of a particular candidate. Just before Election Day, a second poll shows only 520 of 1,000 randomly chosen registered voters expressing the same preference. Is there sufficient evidence that the candidate's popularity has decreased? So from there, again, we want to state, okay? And so we would state that the parameter is the change in proportion of the supporters of this candidate based off of all voters. We would say, we would list what P1 and P2 are going to be in this case. So we want to let proportion 1 be the proportion of supporters on the first poll, and proportion 2 be the proportion of supporters on the second poll in this case. And what we are trying to determine is our null hypothesis is that those two proportions are equal to one another, whereas our alternate hypothesis is that proportion 1 is greater than or equal to proportion 2. You can also write that as P1 minus P2 is greater than 0. Either way works. If you were trying to say that proportion 2 is greater than proportion 1, you could also say that P1 is less than P2. You could also say that P1 minus P2 is less than 0 in this case. Either way works. It doesn't really matter which way you write. Okay. Next, we want to plan. So we want to check all of our conditions. We are told that the voters are randomly chosen. We will assume that 800 and 1,000 are less than 10% of the total population of all voters respectively, and the sampling distribution is approximately normal because the large counts condition is met in this case. So because 460, 360, 520, and 480 are all greater than 10, we can say that that condition is met. We got 460 based off of this and 520 based off of this, so those two were found just in the problem. Then we took 800 minus 460 to find 360, and we took 1,000 minus 520 to find 480, and that's how we found our proportion for success versus our proportion for failure in this case. From there, we would run a two-proportion z-test, so that's going to be our do, and again, you can find that in stat, tests and 2 prop z, not int, test, 2 prop z test. Okay? Or not 2 prop, 2 sample, excuse me. Or no, that's right, 2 proportion. No, it's 2 proportion, sorry. 2 proportion z test, yes, that's right. Okay, and then from there, we would include our x1 of 460 in this case. Yes, so 460. Our n1 of 800. So 460, 800. Our P2, or X2, excuse me, X2 of 520. And our N2 of 1000. Okay. Go ahead and put that in to make sure that this actually works correctly. And we are looking to see that P1 is greater than P2, and then from there we can calculate, and that should give us everything that we need. So we should get a test statistic, so make sure that you name the test, enter the test statistic as Z, which is 2.33. Our p-value is going to be 0.0100, or just 0.01, basically. And so after that, we can conclude. So since 0.01 is less than 0.05, we would reject the null hypothesis and say there is convincing evidence to believe that the proportion of voters who support the candidate has decreased from the first poll, in this case. So now let's look at tests for means in this case, which are going to be slightly different but very similar to proportions. So again, if we're only given one population, we would say that the mean that we're given in the problem represents our sample mean, and then our population standard deviation, or whatever standard deviation we're given in the problem, divided by the total number, or the square root of the total number in the sample, is going to represent our sample standard deviation, whereas a difference in means, we would just take the difference from mean 1 minus mean 2, and the standard deviation would be the standard deviation of sample 1 squared divided by the total number in sample 1 plus the standard deviation of sample 2 squared divided by the total number in sample 2. Take the square root of all that, and that gives us our standard deviation in this case. So let's take a look at this example. A sales representative believes that his company's computer has more average downtime per week than a similar computer sold by a competitor. Before taking this concern to his director, the sales representative gathers data and runs a hypothesis test. He determines that in a simple random sample of 40 week-long periods at different firms using his company's product, the average downtime was 125 minutes with a standard deviation of 37 minutes. However, 35 week-long periods involving the competitor's computer yield an average downtime of only 115 minutes with a standard deviation of 43 minutes. What conclusion should the sales representative draw? So, again, state, and again, this doesn't have to be done in this many lines, but you need to include the parameter, which is the difference in the mean downtimes of each product from all computers from both companies. We need to define what each mean is going to be. So we want to say let our mean of HC be the mean downtime of computers his company is using, and the mean of CC be the mean downtime of the computers this competitor is using. And so our null hypothesis would be that the two means are equal to one another, and our alternate hypothesis is that the mean of the downtimes of computers that his company is using is going to be greater than the mean downtime of computers the competitor is actually using in this case. From there, we want to plan. So we are told that both samples are simple random samples. We can assume that 40 weeks and 35 weeks are going to be less than 10% of the populations respectively, and we can treat the sampling distributions as approximately normal since the central limit theorem applies to both samples. Because 40 and 35 are both greater than or equal to 30, then that central limit theorem is met. And again, that central limit theorem can only apply to problems that deal with mean, not proportion. Okay. From there, we can complete our do portion, which is to run a 2-sample t-test in this case. So you can find that under stats, tests, and let me make sure I get there. We want to run a 2-sample t-test in this case. So 2-sample t-test. Okay. Again, hopefully understanding that t goes along with problems that have to do mean will help you to remember which function you're actually using in the calculator. So when we're given that, what we want to do is we want to enter in our data for this. So let's see. We're told that 40 is going to represent our 30, so our average downtime, so what we enter in for x1 is going to be 125 in this case. So 125. Our standard deviation for that goes along with that is going to be 37, so we're going to enter in 37 for that. And the total number in that sample is going to be 40 for this case. Okay. Let's see. Yeah, that's right. Let's see. Our second sample mean is going to be 115. So, sorry, enter 40 in for that. Then 115 for our second sample mean. Our standard deviation is going to be 43 minutes. And our second sample has a size of 35 in this case. What we are wanting to do is we are wanting to say that our mean of sample 1 is greater than our mean of sample 2. Go ahead and hit calculate right there, and that should give us our exact values for that. So 43 at a sample of 35, and then after you've entered in those values for that test, it should give you everything you need. So you want to make sure you include 2-sample t-test, which again can be covered based off of the function in the calculator that you use. You want to make sure that you include t, which is 1.072, as well as p, which is 0.1438. With a degrees of freedom, you want to make sure you include degrees of freedom. Okay, from there, you want to, once you found your p-value, you want to say that since our p-value, or our conclusion here, since our p-value of 0.1438 is greater than 0.05, or our significance level, we will reject the null hypothesis, and there is not sufficient evidence to believe that there is a difference in the mean downtime of computers his company is using and the computers his competitors are using as well. Okay, so from there we can take a look at chi-squared tests in this case, which are very similar to significance tests for proportions or means in this case, but they have a few differences. So again, when we're looking at chi-squared tests, state the null and alternate hypothesis, and how you do that is for a chi-squared goodness of fit test, we would say that all proportions match the population proportion. So population proportion for the sample proportion for 1 matches population proportion for 1, sample proportion for 2 matches population proportion for 2, so on and so forth. But you can simply say that through just those words right there. Our alternate hypothesis would be that at least 1 does not match the population proportion. Then when we're looking at chi-squared tests for independence, we would say that our null is that there is no association between the two variables, and our alternate is that there is an association between the two variables. Then our chi-squared test for homogeneity is there is no difference in the distribution of the outcomes of the variables, whereas there is a difference of distribution of the outcomes of our variables for our alternate hypothesis. And when we're calculating our test statistic and p-value, our chi-squared test statistic is basically the sum of our observed value minus our expected value squared divided by the expected value. So the sum of all of those instances right there is going to represent the test statistic for chi-squared tests in this case. We're also looking at least squared regression tests. You want to state the null and alternate hypothesis by saying our null hypothesis is that the slope of the population regression line is equal to 0, so there's no correlation between the explanatory and the response variables, whereas our alternate hypothesis is that the slope from the population least squares regression line, or beta, does not equal 0. So there is some correlation between the explanatory and the response variable in this case. And then when we're calculating the test statistic and p-value, it's going to be t is equal to the slope for our sample least squares regression line divided minus the slope for our population least squares regression line divided by the standard error of our sample least squares regression line. And how you find b is r times the standard deviation of y divided by the standard deviation of x, and our standard error of b is going to be s divided by s of x times times the square root of n minus 1. And then s is going to be this formula right here. When we're looking at our AP exam tip for that, the AP exam formula sheet gives the formula for standard error of the slope as s of b of 1. The numerator is just a fancy way of writing the standard deviation of the residuals at s, and the denominator is the squared standard deviations, or the sum of the squared standard deviations in this case as well. Okay, so just a summary of everything for significance tests. Important assumptions and conditions always must be checked before proceeding with a hypothesis test. The null hypothesis is stated in the form of an equality statement about a population parameter, while the alternative hypothesis is in the form of an inequality. We attempt to show that a null hypothesis is unacceptable by showing that it is improbable. The p-value is the probability of obtaining a sample statistic as extreme or more extreme as the one obtained if the null hypothesis is assumed to be true. And when the p-value is small, typically less than 0.05 or 0.10, we say that we have evidence to reject the null hypothesis. But for the most part, you're going to be using 0.05 in this case, if they don't give you a significance level at that point. A type 1 error is the probability of a mistakenly rejecting a null hypothesis. A type 2 error is the probability of mistakenly failing to reject a false null hypothesis. And the power of a hypothesis test is the probability that a type 2 error is not committed.